In this video, we will discuss how we can use the symmetry of a function, i.e. even or odd, to help evaluate definite integrals. And this is going to be specific to definite integrals centered at the origin, i.e. going from minus a to a. So first, if f is an even function, the integral from minus a to a, where a can be any number you would like, is going to be 2 times the integral from 0 to a. Let me just illustrate why this is going to be true. An even function is symmetric about the y-axis, which means it's a reflection of itself about the y-axis. So a typical graph of an even function, might be something like this. And if you look at the area enclosed underneath this graph, so the entire area, because it's a reflection of itself, is going to be twice what happens from 0 to a, which is where this 2 comes from. If it's an odd function, then the definite integral from minus a to a for any a value is going to be 0. So if we consider kind of a typical odd function, maybe something along these lines, the observation is that because it's symmetric about the origin, if you look at the area enclosed, say, above the x-axis in this picture, it's exactly equal to the area enclosed below. So we think of this area enclosed above, we take the positive of it, the area enclosed below the negative, and they exactly cancel each other off to get back 0. So let's look at a few examples. Let's use symmetry to evaluate the following. So the first is a definite integral from minus 5 to 5, so it has to be of this form, minus a number to the number, of x to the 5th over x squared plus 4. If we think back to a bunch of previous examples that we've encountered, where we've checked functions to be even or odd, having x to the 5th, which is odd by itself, over x squared plus 4, which is even, is going to result in an odd function. So let me just note that the function f of x equals x to the 5th over x squared plus 4 is odd. The reason why is if we take f of minus x, that's going to be minus x to the 5th, divided by minus x squared plus 4. Minus x to the 5th is minus the x to the 5th. Minus x quantity squared is just x squared. And what we end up with is minus the function f of x. So f of minus x equals minus f of x. That is the definition of being odd. So from our previous slide, because it's an odd function, and it's an interval symmetric about the origin, the value of that integral is simply 0. So let's look at the second example, and let me remind you when we talked about properties of the trigonometric functions, we said sine is an odd function and cosine is an even function. So if we break this up into 2 separate definite integrals, so minus pi to pi of sine plus the definite integral from minus pi to pi of cosine. And note, we cannot apply these symmetry properties to just any old integral. We need to have one of this form, symmetric about the origin. So sine is an odd function. The interval is symmetric about the origin. So the first integral is 0. The second integral, because cosine is even, this will be 2 times the integral from 0 to pi of cosine. And we evaluate this resulting integral with the fundamental theorem of calculus. An antiderivative of cosine is sine, and we evaluate this from 0 to pi. So we plug in pi, we put a minus sign, and we plug in 0. And in this case, sine of pi, a common value is 0. Sine of 0, another common value is 0. And 0 minus 0 is 0. So let's look at a couple more examples where the symmetry will become extremely useful in terms of evaluating the integral. So for this first example on the slide, absolute value x plus 2. I want to note that that is an even function. And the reason it is even is you just think when you plug in a negative value, you get the same thing as you would for a positive. F of minus x is the absolute value of minus x plus 2, which is the absolute value of x plus 2, which is f of x. So whenever f of minus x equals f of x, that's a definition of what it means to be even. So you might say, well, why is this useful here? Well, if we look at evaluating this, it becomes 2 times the integral from 0 to 1 of the absolute value of x plus 2. And now that we are looking at the absolute value function, in our inputs, the x's are between 0 and 1. The absolute value of a positive number is just x. So we can really simplify that integrand down to something that we can now handle. It will be 2 times the definite integral from 0 to 1 of x plus 2. And the big reason here is because, just note, if x is positive, this implies that the absolute value of x is simply x. So now we evaluate with the fundamental theorem of calculus. An antiderivative of x plus 2 will be 1/2 x squared plus 2x, and we evaluate from 1 to 0. So we plug in 1, put a minus sign, and we plug in 0. And when we plug in 0, we get back 0. So we're going to end up with 2 times 5/2, which is the number 5. Let me also make an observation about this problem that using the symmetry is a convenient way to rewrite it so that we can apply the fundamental theorem of calculus. But we could have done this previously as well. You can think of that geometric interpretation of how much area is enclosed. So an alternative approach would be to sketch the graph and then use geometry to calculate the enclosed area. So one last example. So looking at the integrand, at first glance, this looks like it would be really difficult to evaluate. But we're going from -1 to 1, so our interval is symmetric about the origin. And I'm just going to make the observation, and I'm going to let you check the details. X over cosine plus x is odd. X squared is even. So if we write this as the integral from -1 to 1, so symmetric about the origin, of the odd function, x over cosine plus x, plus -1 to 1 of the even function. The first integral by our property is 0. The second integral is 2 times 0 to 1 of x squared. And in a case like this, going from -1 to 1 of x squared to 2 times 0 to 1 x squared, I'm not sure how much that helps us, but where it does make it a bit simpler is instead of having -1 as a lower limit, you have 0, which is typically maybe easier to plug into an antiderivative. So an antiderivative of x squared is 1/3 x cubed, and we evaluate from 1 to 0. If you plug in 1, you get 2/3. Subtract away what you get when you plug in 0. So the value of this definite integral using symmetry was 2/3.